Hello everyone, and thank you for coming today. I'm Sam Knight, an application engineer here at Yaskawa America Incorporated. Today I'm going to be giving you an introduction to Sigma-7 FT62 high-speed position output servo packs. I'm going to be trying to answer all of your questions throughout the presentation today, but if there's anything that I gloss over, or if there's anything that you would like more detail on, we have a couple of really good resources. First is the FT62 manual. This is where you can go to get specific servo pack ratings and specifications, as well as more in-depth descriptions of the output settings. You can get this on the Yaskawa website. We also have an application note that we wrote. This includes a lot of specific application examples, as well as some timing considerations. These are important if you're designing your own FT62 application. And then finally, we have the Y Digital Cam Switch help file that can be found in MotionWorks IEC or online. The Y Digital Cam Switch block is our newly modified FT62 cyclic application block, and we'll be talking a lot more about this later on in the presentation. So here's our agenda for this whole talk. We're going to start by talking about FT62 basics. This will just be kind of what FT62 is, why you might want to use it, and some specific system specifications. Then we'll be talking about output settings. This is how you configure an individual output. Then output configuration. This is how you'll actually set the output settings within the servo pack. Then we'll go on to toolbox support to talk about the function block that we've created to make FT62 easier to use in MotionWorks IEC. We also made a simple test setup that can be used to verify your application before putting it on a machine. And then we can show you a short application example of FT62 running inside of MotionWorks IEC. So we'll start with FT62 basics. The first question we want to answer is, what is FT62? So FT62 is a specific firmware and hardware variant of the Sigma-7 servo pack. Right now it's only available for Sigma-7. You can tell that it is FT62 by the F62 appendix to the model number. What FT62 allows you to do is define an absolute encoder position where an output will be triggered for a duration that's specified by the user. And these outputs occur at a very rapid rate because they are completely independent from the controller. Once the controller defines the position on the servo pack, the amplifier will look for when the absolute encoder position passes the position that was defined, and then output a digital output, which is it does not require response from the controller to be set. So there's no latency in the communication time between the two devices. And you might be asking how much faster these actually are, and they've decreased in speed from the standard outputs, which are available on all servo packs, at about 1 to 2 milliseconds output time. They've decreased to only 1 microsecond of delay time. And this is possible because of the specific hardware that they use. The encoder outputs have been repurposed from the traditional servo pack to act as high-speed outputs. So if you have an application that requires reading these encoder outputs, FT62 will not work for you. They've also decreased the output variation quite significantly by about 25 times, from 125 microseconds to 5 microseconds. So not only will these outputs trigger much more rapidly, they will also trigger much more precisely. So when you're doing FT62, you have access to 2 output terminals, and this is a good time to talk about the difference between output tracks and outputs in general. So if you think about a music box, you have a track for every note. So if you have 5 notes, like here we have 5 possible output terminals on the drive, 2 high-speed output and 2 standard speed outputs. And amongst these tracks, you have positions that you can define. So on a single note, you might have 5 pins that strike the note, and that would correlate to 5 individually defined positions. And these 32 positions for high-speed output and 32 positions for standard speed can be defined in any configuration. So you could have 15 on HSO1 and 17 on HSO2, or 32 on HSO1 and 0 on HSO2, and the same goes for standard speed outputs. And as we said previously, this performance increase is due to the fact that the FT62 drive uses line drivers for its outputs instead of photocouplers, or I should say in addition to photocouplers. The next thing we'll talk about is how an individual output is configured in drive memory. These output settings there's 5 output settings in total, and the very first of which is output function. The output function is a single byte that's written to the drive, and it can be broken into 4 parts. We'll only talk about 3 of them because one of the parts is used to define the axis number, which can be called axis type. And since we're only using Sigma-7 S drives at the moment, this can just be ignored. But the first of the 3 types that we'll be talking about is output terminal end type. This is how you define whether or not you're using a high-speed or standard speed output, and from which terminals the output can be seen. It also controls signal logic, which determines whether or not a signal is active high or active low. And then we can define passing direction, which defines whether or not the axis will give out an output when spinning in the positive direction, or the negative direction, or in either direction. The next setting we have to talk about is output position. And to understand output position, you need to understand the units that it's programmed in. And this is programmed in absolute encoder pulses. This value can be read from the option monitor at 1312, which is configured on the drive using Y-write drive parameter. So if you write value 10 to parameter number 825, you'll be able to read the lower 32-bit encoder count on option monitor 1312. If you were to graph this while the motor is spinning in the forward direction, you would see this diagram. You can see encoder pulses on the y-axis and time on the x-axis. And this value ranges from negative 2 to the 31 to 2 to the 31. You can see it increasing in the positive direction, and then once you reach the maximum value, it will roll back down to the negative direction. So to define a position, we simply have to choose a value at which we want the output to become active once it has been crossed. So we'll arbitrarily choose a value of approximately 0 and put an output position on the graph. Once you have a position defined, you need to define a duration. There are multiple methods to define duration, but the first of which is output distance. Output distance is defined as the number of encoder pulses after the output position has been passed that the output will remain active. We can see here that the output distance is simply a value in the positive direction for which the output will remain active while the axis is between those 2 points. An important consideration for choosing output mode is to consider how velocity will affect the duration of your output. So to consider this, we'll overlay another graph over this one. The graph you see here in red symbolizes an axis spinning at a higher velocity. You can see it's compressed in time, so more encoder pulses are covered in less time. So it's simply a motor spinning at a higher rate. So we'll separate these graphs and translate the output position to the lower graph. And if we want to figure out the duration of this output now that we're traveling at a higher speed, we need to figure out how many encoder pulses are covered by the output distance. So we'll measure vertically how many encoder pulses are covered by that output and translate it down to the bottom graph. And you can see here that the duration of these two is not the same, even though the number of encoder pulses was identical. So this is important in considering choosing the distance output mode. You can see here that even though the number of encoder pulses was the same, the duration is much different. So if you had an application that required an output to be on at the same point in every cycle, output distance would be a good method to choose. However, if you required it to be on for the same duration, then output distance would not be the correct method to choose. The next method for defining duration is output time. And output time is defined a little bit differently depending on if you're using high-speed or standard speed outputs. If you're using a high-speed output, output time is defined in microseconds. If you're using a standard speed output, output time is defined in milliseconds. So we'll do the same exercise we did previously to determine the behavior of this output mode when velocity changes. So we'll put the high velocity graph back on and translate output position down. And this time we can also translate output time down because it's a constant duration. So you can see here that even though the number of encoder pulses traveled is drastically different, the duration is identical. So this is very useful when you have to trigger something that requires an output to be active for a certain amount of time to execute, regardless of when it actually turns off. So this would be good for, say, triggering a camera. If the camera trigger needs to see a signal for 1 millisecond to register taking a picture, then this mode would always output for 1 millisecond regardless of how fast the axis is spinning. It would, however, always turn off at a variable point depending on the speed of the axis. To choose between these two output duration modes, you can set PN660 by using wide right drive parameter or by using Sigma-7 Plus, and we'll talk more about that later. But you can also see that the high-speed outputs and normal speed outputs can be configured to use different output types. So high speed could be configured to use time, and normal outspeed could be configured to use distance at the same time. The last setting we should talk about is output position compensation. And what this allows you to do is compensate for latency in a machine. So output position compensation is also defined in absolute encoder pulses. We can see here we define it as a small negative offset. So if you have a device which intrinsically has some delay, we can say maybe a solenoid coil actuating a blow-off valve. By adding a small negative position compensation, we can create a new effective output position that is shifted slightly backwards in position. We can see that here. So then by the end of the output cycle, at the effective output of your machine, we can see that it's outputting at exactly the time that we want. So now that we've configured all this, we can see a simple instance of it running. We've defined at the bottom left an initial position with the axis starting at that initial position. And then once we start it rolling forward in the positive direction, once it passes the effective output position, we will see the output come on and stay on until it reaches the end of the output duration. And the settings are as simple as that. So we'll continue on now to talk about how we configure these settings in memory. And it's important to note right off the bat that these are configured in drive memory. These are not parameters that you set. These are physical memory addresses that you write to. So there are 3 methods for setting these values, the first of which is through Sigma-7 Plus. It's important to note that to do this with Sigma-7, you need to download Sigma-7 Plus version 7, and that's available free off the website. You need version 7 because that's the first version which can recognize FT62 drives. So there are other resources which discuss how to connect Sigma-7 to your servo pack. So I won't talk about that at all. But once you do get it connected, you should see this menu. Then you can go down to the diagnostic section and click on Set Triggers at Preset Positions. And this will open the FT62 dialog. You can see it here. At the top, you can choose between high speed and normal speed outputs to configure. And then you can just set the values that we talked about previously in the window as you please. Once you're done setting these values, you'll go to the top and click Write Edited Parameters to the servo pack. And it should be as good as that. These positions will be set in memory, and you can use them. It's important to know that some of these values, however, require a power cycle to be taken in. And those include the axis number and the output terminals and signal logic underneath output function. And for these values to be taken in on power cycle, it's required that they're saved into non-volatile memory. So to perform that, all you need to do is write all edited parameters to the servo pack and then click Save to Flash Memory. You also need to know that the motor cannot be enabled while you're trying to save to flash memory. You can set PN660 through Sigma-7 as well if you're trying to choose the output mode type, and you can do that by simply going to the basic functions and clicking Edit Parameters, and then setting it the same way you would set any other parameter. PN660 can be seen if you have Sigma-7 connected to an FT62 drive, but it won't be available if you're not connecting to an FT62 drive. Oh, and quick note on that as well. It's important to note that changing PN660 also requires a power cycle before the values will be used by the drive. The second method for configuring these output settings is through direct memory access using these 2 new blocks. We've created the Y write drive memory and Y read drive memory to allow FT62 programmatically through MotionWorks IEC. These blocks have an address input, which corresponds to a large memory table that can be found in the FT62 manual. You then set the data type, which dictates the size of the data you're trying to write. You can see on Y write drive memory, there's an option for mode as well, and we'll talk about how that's used in a second. Here we have a small snippet of the memory table that you can find in the FT62 manual. It looks pretty busy, but if we take out all the extra noise, you can see it's simply the 5 settings that we talked about previously. When using these blocks to write drive memory, if you're writing output function, you will still need to do a non-volatile memory write the same way you did previously in Sigma-7. The way you do this with these function blocks, though, is a little bit more complicated. I won't go incredibly into depth on how to do it, but I can show you this table here. So if you want to perform a non-volatile memory write, you have to perform a sequence of 6 Y write drive memory executions using these exact values. You can see here on the right that mode is set to 2, and that means that the blocks are being used to perform a non-volatile memory write. After you perform that action, the drive will need to be power cycled to take in the new function values. The final configuration method is a little bit different than the others because it's optimized for cyclic applications. The first 2 methods I showed you through Sigma-7 and through the function blocks are very good if you want to set a single absolute encoder position at which you want an output to occur. So that's very good for linear applications because it will always be in the same place every time. However, if you're constantly spinning forward, it's important to be able to update those absolute encoder positions to the next cycle. And that's where our support for FT62 comes in our PLC Open Toolbox. So we have updated the Y digital cam switch block to include some FT62 code. This block can be found in the PLC Open 340 toolbox. And if you get the newest installer, then you'll have the FT62 functionality. To know if you have the correct toolbox, you can go into the version number in MotionWorks IEC, and you should see that it's at least version 3.4.2. That will include all the newest FT62 code. This block does a couple really important things for the user. The most important thing that it can handle is it allows the user to program in user units. So previously, everything we were programming was done in absolute encoder pulses. So you could say, I want there to be an output at 2 million encoder pulses, but it was difficult to translate that into something with physical meaning in MotionWorks. So what you can do with this block now is you can define a machine cycle in the hardware configuration, and then you can say, I want there to be an output at, say, 5 degrees in my 360-degree machine cycle, assuming we defined a 360-degree machine cycle. And then every time that 5 degrees is passed, you'll see an output, and it will automatically handle updating with the machine cycle. So every time you pass 5 degrees, it will add a machine cycle to your absolute encoder value that you're writing to the drive, and then write that for you automatically. So you'll never have to handle updating due to the machine cycle. It also includes the entire memory table internally, so you won't need to access that or even look at that in the book. And it handles the encoding of the output function byte. So we talked about it previously, how it can be broken up into 4 pieces. But this is really a single byte with many bits that each have individual meaning, and this block will handle all of that for you. Important to changing the output function as well, we discussed that some of the values require a non-volatile memory write and some of them don't. But Y digital cam switch will handle all of that for you. So if a non-volatile memory write is required, it will output an error for you. And this error code is 10223, and that will indicate that a power cycle is required. And power cycle management, it tells you when a power cycle is required. So these are the old data structures that were used for Y digital cam switch before we updated it to include FT62. So we've repurposed a number of these values to mean something else if you're using an FT62 drive. So these are the values that apply to FT62. I suppose now is a good time to say as well that the Y digital cam switch block will automatically detect if you're using an FT62 drive. So if you're using a drive that is not FT62, it will use the previous functionality, but if you do plug into a drive that is FT62, it will detect that and it will start using the high-speed output functionality. So we can break down this data structure a little bit and talk about what some of these things mean. The track number is used to define whether or not you're using a high-speed or standard speed output, and from which ports these outputs will be visible. The first on position is defined in user units, and it dictates the output position. So this would be where you would say perhaps 5 degrees in a 360-degree cycle. That was where your output would occur. The axis direction determines how your output will be triggered, whether in the positive, the negative, or either direction. Cam switch mode determines both your output type, the PN660 setting, and whether or not it will be active high or active low. Duration, as we discussed previously, is defined differently whether or not you're using a high-speed or standard speed output, so either in microseconds or in milliseconds, and that's just a D-int. And then distance and on-compensation scalar are both in user units, and on-compensation scalar is equivalent to output compensation value. So we also created a test setup, which can be used to verify your application, because it's important to know that you can't see the value of your output in MotionWorks IEC. It's happening at such a quick rate that even if the controller could read that pin, it would be an inaccurate value because the scans are occurring at a millisecond rate and these outputs are occurring at a microsecond rate. So we developed this quick self-latching circuit that you can use to see exactly the position at which your servo pack had an output. You can see here we've wired pins 17 and 18, which are the high-speed output ports HSO1, into a level shifter, which takes the 5-volt output signal and translates it into a 24-volt signal that can be used to latch the servo pack. And then you just need to apply power to the I/O pin 6, and this allows you to detect rising and falling edges of the high-speed output. And then using the function blocks MC touch probe or the product buffer, you can see the actual output positions in MotionWorks IEC. So this is the setup we're going to be using to show our application example in a short second. So now I can show you guys FT62 working in MotionWorks IEC. So I'll quickly close it on my PowerPoint and open up MotionWorks. The first thing you're going to want to do when creating an application for FT62 in MotionWorks IEC is to define your data types. So as I showed you previously, there are 2 structures that we'll need to fill out for wide digital cam switch. The first of which is this cam switch ref structure. So you can see here we've defined the track number as 1, which means that it's the high-speed output terminal 1. We've defined the cam switch mode as 1, which means that it's in time mode and it's an active high signal. We've defined the axis direction as 0, which means that it's triggering in either direction. And we've defined the first on position as 5. And we actually have a machine cycle of 20, which is defined in our hardware configuration previously. We don't define the distance below because we're in time mode, and it's not required that you define distance. If we had defined it, it simply would not be used. Then we've defined the duration below as 10,000, and because we're using a high-speed output, this is 10,000 microseconds. Below, we've initialized the on-compensation scalar to 0. We'll show what changing this looks like in a short moment. And then we've configured the self-latch down below. So if we go into the main application here, I'm going to quickly warm start the drive, warm, stop, warm, just to make sure everything's initialized. Then I'll turn on our axis. It's good to know that you can enable wide digital cam switch whether or not a move is already active, and it should be accurate. So I'm just going to go ahead and start a move, and then enable wide digital cam switch. You'll notice that it immediately went to in operation. This is because I've ran this block previously. If you hadn't run this block previously and you were setting this up for the first time, you can remember that a non-volatile memory write and a power cycle would be required. So the first time I enabled this on the error ID, you would see error 10223, and that indicates that a power cycle is required. If we go down here now to MC touch probe, we can see that it's latching at approximately 5. And every time the position rolls over at 20 and comes back to 5, we'll see a new latched position. And that's because it's handling the cyclic position update for you. This small little offset you can see here, 0.00009, is due to the latency of the level shifter that we're using. It has some internal photocouplers, so there's a small amount of delay there. But if we want to get rid of that, we can simply observe the value in user units and then add that much compensation. So I've already added it here, negative 0.0009. So we'll shift, and you'll see that we're now almost exactly at 5. And if we want, we could set it back by clearing it out, and it will apply the next time an output is detected. So there's a question here that says, if an output is set for distance duration mode, can you also set a maximum on time? And the answer for that right now is no, you cannot. It's actually important to note that if you're using time duration mode as well, and you're spinning too fast, which causes a single output to overlap itself, the FT62 drive will lock up. So it's important to keep track of the output values that you're using and monitor the speed that you're using as well. I see a question that says, is it possible using MotionWorks IEC to update start and stop positions on the fly without requiring a power cycle? That's a really good question. It's possible to change passing direction, output position, output distance, output time, and output position compensation on the fly without a power cycle. There's a question again to clarify how many high-speed and normal speed outputs there are. There are 32 high-speed outputs, and there are also 32 normal speed outputs. And then if we want to talk about tracks, there are 2 high-speed output tracks and 3 normal speed output tracks. So those 32 outputs that are available can be configured amongst their output tracks however you please. So there's a total of 64 outputs that can be configured. There's a question, is the distance value absolute from 0, or is it relative from the start position? I assume this is talking about the distance setting. That's relative from the output position. So if you define the output position at 1000 and then define the distance as 1, the output will be on between 1000 and 1001. Okay, and with that, we're going to wrap it up. Thank you all for your questions. If you have any more, you can email me at sam_knight. My name is on the first page of the slide, so you can maybe look back when the webinar is posted. And I will attempt to answer any more questions you have. Thank you very much. Bye.